Howdy folks. In this video we're going to review a basic alpha measure in the component method. In a previous video we built a pretty simple measure that did a row count of our stores table, and in this video we're basically going to take a look at it and spend a bit more time thinking about how it works and how alpha measures work in general. So if you haven't seen my spiel about the component method has two parts to it. There's components and there's patterns. So components are like parts of speech in grammar. So in the same way that an English sentence is made up of nouns, verbs, and adjectives that all sort of work in concert to create sentences, DAX expressions are made primarily up of filter refiners, table derivations, and iterators, which also sort of work in concert to create meaningful numbers and tables in DAX. So filter refiners set up the filters. The table derivations will create a temp table based on those filters, or ignoring the filters if you tell it to. And then an iterator will take a temp table and then turn it into either a number like total sales or into yet another temp table like just the days in 2016. So those are the components. The patterns are common ways of bringing those components together. So in the same way that here we have three completely different English sentences, they're all made up of the same parts of speech assembled in the same way. They're all a noun followed by a verb followed by an adjective. So over here, even though we have two different DAX expressions that do completely different things, they're all sort of built in the same way. They all have a table derivation inside of an iterator inside of a filter refiner. That's true in this version, and it's true down here. So right there's the table derivation in both of them. There's the iterator in both of them. And there's the filter refiner in both of them. Okay, so that's sort of my quick spiel. If I come over here to the example section, we can go quickly look at the measure we built in the last video. So I'm going to twirl open fields over here. If I twirl open measure and then click on this measure, it used to be called mystery measure. I've renamed it number of stores, mainly so it takes up less space. This is a measure that counts how many stores are visible for a particular cell. Okay, so if I were to tell you that this is my stores table in my data model, this is like the actual table of stores that I have in my organization, in my little fleet of coffee shops, and I would also tell you here's the number of stores broken down by state, by layout, and by city and layout, you'd look at these numbers and you'd look at this table over here and you'd say, yep, that sounds about right. If I were to say that there's 4 stores in Oregon, well, sure enough, there's 1, 2, 3, 4 stores in Oregon, 2 in Washington. Yep, they're right there. If I were to say that there are 3 stores that are sit-down stores, well, there's 1, 2, 3. Yep, that makes sense. And 3 walk-up stores, well, 1, 2, 3. Yep, 3 walk-up stores. Okay, so for a decision maker, these numbers are completely correct, right? But we want to think a little bit about where they came from, right? Why are they correct? How is this happening? And to cut to the chase, it's a combination of filter refiners, table derivations, and iterators working in concert. Okay, so if I think about this cell right here for a number of stores in Oregon, right? That's how a decision maker would interpret this cell right here. How does it work? Well, if I look up here at the code, here's the code for that particular measure, number of stores. There it is, number of stores. The very first thing the measure is going to do is refine the filters, because that's what every measure does. If you don't like that, too bad. You can't turn it off. Whenever you run a measure, the very first thing it does before it does anything else, before it runs any code inside the measure, is to refine the filters, right? To create a new set of filters to determine what's visible in my physical tables, okay? So for this cell right here, right, when it starts evaluating, the measure is going to refine the filters, and when you refine the filters, there's sort of 2 things that happen. There's going to be automatic current row filtering and optional override filters. Now, we haven't provided any override filters, and you tend not to do that with measures, but we are in a row, right? So if I look at this cell right here, the current row has the categorical value of state equals Oregon in it. So the measure, right, before it runs any code, creates a new filter context. If I'm thinking of this cell right here, it's going to create a new filter context with the filter of state equals Oregon in there, right? Now in DAX, filters are tables, so the actual filter would look something like this right here. If we just had the state and the Oregon part, we didn't have Washington or this column right here, it would just be a little teeny tiny table that said state equals Oregon. It would go there in the filter context. And with state of Oregon there in the filter context, suddenly in my physical table I have a new set of visible rows, right? Before the measure added that filter of state equals Oregon, I could see all the rows, right, here in my physical table. As soon as the measure performed current row filtering to refine the filters, to add the filter for state equals Oregon, now I am just looking at the Oregon store. So the visible rows are going to consist of these first 4 rows right there. These last 2 rows are invisible, right, between these 2 lines in the code, right? And I should say, like, technically you can see it up there, but basically anywhere in the code, unless I use another filter refiner to create a new filter context, right, I'm going to be looking at those default filters introduced by the measure. Okay, so we just said that this measure is going to add a filter of state equals Oregon, right? It's going to be true for the entire measure unless I use another filter refiner. So between this line and this line, if I'm thinking about this cell, I'm just looking at Oregon, okay? So I've refined the filters, and now I'm going to derive a table. So my table derivation is right there on line 4, dim stores. Now notice I have 4 different common table derivations. I can ask for a table, I can ask for the values of a column, I can ask for all of a table, and I can ask for all of a column. These first 2 up here respect the filters, and these 2 down here ignore the filters. This one and this one give you all the columns of a table. This one and this one just give you all the distinct values of a single column. So when I ask for dim stores, that's going to be this first version right here, where we get all the columns of a table, but just the visible rows, because this version respects the filters, right? Well, what do we have in filters right now? Well, I just told you, we have a filter for state equals Oregon, right? So when I derive this table right here, the temp table that is produced is just going to include these first 4 rows. It'll be all of the columns, but just the first 4 rows, okay? So that is what is produced by line 4. So now we have a temp table, right? So now we're going to take that temp table and pass it into an iterator, right? Well, what iterator are we going to use? SumX. Now, there's several iterators we can use: SumX, AverageX, MinX, MaxX, filter. There's even more. These are the most common ones, right? But we're going to use the SumX function. And what is an iterator going to do? Well, all iterators behave the same way. They add a column to the temp table, right? And then they produce a new value with the results. That new value can either be a single number, or it can be a temp table that is changed in some way or improved in some way. Okay, well, what is the SumX iterator going to do? It's going to add the following column with the definition of just the number 1 to this temp table, and then it's going to sum up the results, right? So if I think this table, this temp table right here, just has the rows for the stores in Oregon, when I add a column with the definition of 1, I'll have a little 1 there, a little 1 there, a little 1 there, a little 1 there. And if I add up 1 plus 1 plus 1 plus 1, because that's what SumX does, it sums up that new column, I'll get the number 4, which is where I get that 4 right there. Okay, so here we've gone through the entire path, right? The iterator added a column, and then it summed it up to produce a number. And that number, right, is going to show up in our summary table right there. Technically, this is a table visual, right? But the table visual and the summary table look quite like each other. If I wanted to take this visual right here, I could have Power BI redraw it as a different chart type, like maybe that chart right there, right? Now, it's being drawn differently, but the same information is being rendered, so it has the same summary table. The nice thing about a table visual is that the drawn version looks an awful lot like the summary table, so it's sort of easy to analyze. Okay, good. So let me click back on my measure to whirl this guy closed. So one thing I'd like to point out, right, we've sort of gone through where we got this number, and I sort of maybe even stole my thunder a little bit. If we think about it, here I've got 4 and 2 and 3 and 3. Here I've got 1 on 1, 2 and 1. If we actually look at our code, right, for every single cell, I run the exact same instructions. There's nothing in this code explicitly that says go do any filtering. There's nothing in this code explicitly that says go look at a particular layout or go look at a particular combinations of city and layout, right? So this could be kind of confusing if you're new to DAX, right? So I've got a number here and I've got a number here. They're both running the exact same instructions. Why don't I get the exact same results? And the reason is the filter refining behavior of a measure, right? So when I call the measure, right, in these 2 different cells, before anything happens, both of the measures add filters for the current row. They perform current row filtering. Now over here, on in this cell right here, when the measure performed current row filtering, it added a filter for state equals Oregon, right? Over here, we'll add a different filter for layout equals sit down. And so now all of the code all of the code in the measure, unless I use another filter refiner, all of the code in the measure will get executed under that new filter context. Not looking at Oregon now, but just looking at sit-down stores. So a different set of rows will be visible in the table, just the sit-down stores. And if I think about what those rows are, it'll be that one right there, that one right there, and that one right there. And I should say it's the entire row. So that one there, and that one there. Okay, so even though I'm running the same code, right, this table derivation is going to do different things in each one of these cells. Why is it going to do a different thing? Because the measure has refined the filters to take any values of the current row and add them as filters to create a new filter context, so we're just looking at the right subset of data, right? So now when I go say, hey, go get a table derivation of dim stores, right, I'm not going to get the entire table. I'm just going to get the dim stores that are sit-down stores. So that new table will have 3 rows in it. I'll add a column to it with the definition of 1, same as before, and then I'll sum it up, same as before, and I'll get 3. I'll get 3 right there as well, okay? So likewise, if I just sort of to kind of beat this to death, if I come over here, right, and I look at, I don't know, let's look at this cell right here. Well, right now, a decision maker would say, yep, we're looking at the number of stores in the city of Portland that are walk-up stores as opposed to sit-down stores, right? So where did we get this number? Well, for an end user, they would say, well, of course, that's how you got the number. I could look at the table over here and say, in Portland, there's two walk-up stores. There's that one right there and that one right there. But how do we do it in the code? So if I think about this cell, right, even though it's the exact same set of instructions as this cell and this cell, in this cell, when the measure starts evaluating, the very first thing it does is it refines the filters. Any measure will refine the filters. All measures will refine the filters. If you don't want a measure to refine the filters, too bad. It always does it, and you can't turn it off. Okay, so in the cell, when we refine the filters, what do we add to the filter context? How are we modifying it? Well, we're going to add a filter for city equals Portland and layout equals walkup. We'll have 2 new filters in our filter context to define a new set of visible rows. Specifically, it'll be the rows that are both in the city of Portland and walkup, which will consist of these first 2 rows right there. That row right there and that row right there, which are both walkup and in the city of Portland. Okay? And like before, we'll add this column to it, and we'll sum up the results, which is where we get the number 2. So if I think of just a table derivation, dim stores, that's visible in that cell, I would just get these first 2 rows. I would add a column with the definition of 1, so I'd get a 1 right there and a 1 right there. And if I add 1 plus 1, I get 2, which is where we get that number right there. Okay, so one last thing on this. If I click on state equals Oregon, right, the numbers change somewhat predictably, right? For one thing, if I look here on the state table, I no longer have Washington. Okay, that's about what I'd expect. The number of stores in both sit-down and walk-up go down because we're just looking at Oregon. We go from 3 to 2 and 2, right? And this changes over here. So I want to briefly go over this because this filter for state behaves a little bit differently than the filter for state down here. Or I should say, it comes from a different place, okay? So if I imagine... Let's imagine, I don't know, what's a good one? Let's imagine this cell right here. This is a nice, easy one. Okay, so if I'm thinking about this cell right here, right, when the measure starts evaluating, there's actually already a filter in place for state equals Oregon, okay? That's been introduced before the measure even got called. Now, for what it's worth, when we created that measure, or when I should say the DAX engine created that measure, it did it through a combination of filter refiners, table derivations, and iterators. But that doesn't really matter too much for us. What matters, right, is this filter for state equals Oregon comes from outside of the summary table, right? So when I think about this cell right here, right, when this cell starts evaluating, there's already a filter for state equals Oregon, but there's not a filter for layout equals walkup, right? And where do we introduce the filter for layout equals walkup? Well, that's what the measure does. All measures are filter refiners. They always refine the filters, and they always perform automatic current row filtering. So if I think about this cell, it starts by having, before the measure even starts doing anything, there's already a filter for state equals Oregon. The measure then says, okay, I need to refine the filters. Are there any categories in the current row? Yep, there sure is. There's a category for layout equals walkup. The filter refiner right, of the measure creates a new filter context that the rest of the measure is going to run in. It goes sort of from here to here. Technically, it actually goes from the start of the equal sign to down there, but the lines don't look as good. So everywhere in the measure, right, is part of that new filter context with both state equals Oregon and layout equals walkup. If I wanted to look at a different subset of the data, let's say I just wanted to look at sit-down stores, I could use a filter refiner to create yet another filter context to look at a different set of visible rows. But here with this basic alpha pattern, we assume that that combination of the external filters from slicers and things like cross-filtering and things like that, plus the current row filtering of the measure, will correctly point at the right subset of data that we want to look at. So when we say that there's 2 walk-up stores and the state of Oregon, I can look back at my table here and say, oh, yep, there's the 2 stores that are both walk-up and in Oregon, which is why I get 2 right there. Because when I derived in stores, I got those first 2 rows as a temp table right there. I passed it into an iterator. That iterator was the SUMX iterator, right? That iterator added a column to the temp table with the definition of just the number 1, right? So we get a little 1 there and a little 1 there. 1 plus 1 equals 2, which is where we get the number 2 right there. Okay, so there's a whole bunch of stuff you can do with these alpha patterns, and they get used all over the place. But I think it's actually quite helpful to stop and just see sort of how the whole thing works. And it's kind of nice because with these basic alpha measures, you could see how filter refiners, table derivations, and iterators work together. Now, at some point, we'll have additional filter refiners to create new filter contexts, which will be super duper cool. But at least here we could see how you need all 3 of them. Refining the filters points at the right subset of the data. Deriving a table creates a temp table that we actually can use to build something. Then we pass that temp table into an iterator to add a column to it and turn it into something like a number, or in this case, the number of stores that are visible in our summary table. Okay, well, I sure do hope that was helpful, and I will see you next video. Quick addendum, you know what I forgot to do? I forgot to define what an alpha pattern or an alpha measure is. How are you guys supposed to learn anything if I don't define my terms? I don't know, that's terrible of me. I'm sorry, I apologize. If you've seen the other videos, you've already seen these. But just real quickly, if I come over here to my patterns overview, come over here to the patterns overview page, the alpha pattern is quite simply any table derivation inside of an iterator. So the table derivation can be any of the 4 table derivations. You can ask for a table, you can ask for the values of a column, you can ask for all of a table, you can ask for all of a column, and then you pass that into an iterator like SUMX, AverageX, MinX, or filter, right? Now this alpha pattern gets used all over the place. So all these other patterns, the beta, the gamma, the delta, the epsilon, all these fun, fancy, cool sounding Greek name patterns, they're all based off of this alpha pattern. So without the alpha pattern, you can't really do anything. It gets used everywhere. But if you have a measure that only has an alpha pattern in it, I refer to that as an alpha measure. So this is generally going to be a pretty simple measure, like how many stores are visible, or what is total sales, or how many customers are there in a particular time period. You could use a basic alpha pattern, or more specifically an alpha measure for that. And again, an alpha measure is just a measure that only has an alpha pattern in it. So if I come back over here to example, and I click on number of stores, see if I can get this thing to render correctly. There we go. So the reason that this is an alpha measure is it's a measure, and the only thing in this measure is this single alpha pattern, right? So I've got my table derivation right there. It could be any of these 4, and I take that table derivation and I pass it into any of these iterators, right? SUMX, AverageX, MinX, MaxX. I could even do something that's not on this list, like median X or stuff like that. But anytime you have a measure that just has a table derivation inside of an iterator, that's going to be an alpha measure, and those are going to be your most basic measures. Okay, well, I do hope that was helpful, and I will see you next video.